In the upcoming few videos, we're going to be talking about curves on algebraic surfaces. Now, why do we want to study curves on algebraic surfaces? They're very nice in the following sense. We can view them. So curves on algebraic surfaces, they are codimension ones of variety, so we can view them as divisors. But also, this is a phenomenon just for algebraic surface. We can define intersection number of curves with curves. And thus we can use intersection theory. In general, one can only define the intersection number of a variety with a variety of complementary dimension. But the complementary dimension of dimension 1 inside an algebraic surface is still 1. So we can define intersection number of two curves. And thus actually we can define intersection numbers of two divisors. And those numerical data turn out to be extremely useful. That is why we have a complete classification for algebraic surfaces, but we don't have an analog for higher dimension. So now, to study curves on a surface, we will study divisors. You are probably familiar with the following notion of divisor in the case that X is a curve. If we want to store a bunch of information at each point, for example, points in fibers of some map, if we want to store the point and the multiplicity inside one object, then we would form a divisor that would be a formal sum of the points. It's required to have discrete support, so on a compact curve it would have finite support. Now, how would we generalize this to higher dimension? Well, there are two ways of thinking about it. We could view these points here as codimension 1 subvarieties of the curve, so that in cases of higher dimension, we just replace them by codimension 1 irreducible subvarieties. That gives us definition of a Weil divisor. Another way we could think about them is that we could think of these as being zeros and poles of meromorphic functions with a caveat. So let us explore that viewpoint, and that will lead us to the definition of Cartier divisors, which are also called locally principal divisors. Let's look at the specific case when X is a curve A1C. Then these points are just complex numbers, and then we can think of this as the divisors of poles and zeros of a complex function. Which function? This rational function. This is the magic of having global coordinates. And in general, in any affine space, every subvariety that is irreducible of codimension 1 will be cut out by a single meromorphic function or rational function. This is like in linear algebra. In linear algebra, every linear function will cut down the dimension by 1, and every codimension 1 subspace arises this way. So here, instead of linear function, we have polynomial. Every polynomial will cut down the dimension of an by 1. So every hypersurface is of codimension 1, and every codimension 1 irreducible subvariety arises this way. All such subvarieties must be hypersurfaces cut out by a single polynomial. How do we find this polynomial? Well, we can just take any f that vanish on C, and then we can factor f into irreducible. So C lies in the union of the zero sets of these, but C is irreducible, so it lies inside the zero of one of these at least. So one of these fi must actually vanish on C. So we just take that fi because these are irreducible, right? And that fi is going to cut out C. So here we see that the key thing we use is that the coordinate ring of this variety is a UFD. The same argument also works for projective space, so we see that codimension 1 irreducible varieties of the projective and affine spaces are hypersurfaces. However, if we replace the affine and projective space by some general variety X, then this is not necessarily true. But not all is lost. Even though we do not have this globally, we will still have this locally. So let me explain what I mean. At every non-singular point P of X, that's also contained in C, we should be able to find a neighborhood U containing X such that over the neighborhood U, C is cut out by F. So why is that? Well, the reason here is that the local ring of the singular point is a UFD. So we can repeat the previous argument, but now locally. We take a polynomial that vanish on C in this dog, and then just look at its factorization in this ring. Alright, so that's what happened at every non-singular point, right? At every non-singular point, C has a local equation. Now then, if X itself is non-singular, or we might say smooth, then we can cover X by neighborhoods U alpha, such that on each U alpha, C has a local equation F alpha. So we can think of C as a set of its local equations, because we can recover C from this. Now, more generally, if we have a divisor D here, and on each U alpha, this Ci has local equation F alpha I, then mimicking the one-dimensional case, we can think of this divisor D as being locally cut out by the product of this F alpha I, product over I, right, for each of these Ci. So we want to define the notion of Cartier divisors to somehow incorporate this. So how would we describe this set? Well, this is a covering of X, and then this is a family of function F alpha that is rational on each of these U alpha. But there are more we can say about this F alpha. These F alpha must be compatible in some way, right? Because they are all local equations of D. On each U alpha, D is just going to be the divisor of F alpha. Now that means that on the intersection of U alpha with U beta, diff alpha must be equal to diff F alpha must be equal to diff F beta, because they are both equal to D. That means that their difference must be zero on U alpha intersect with U beta, but that's just the divisor of their quotient. So their quotients have no poles or zero, so their quotient must be a unit on U alpha beta. So that would be the definition of a Cartier divisor. It's going to be a family of a pair like this. F alpha is a rational function on U alpha that are compatible in the following sense. F alpha over F beta should be a unit inside this ring. In other words, they should be regular and non-zero on the intersection of U alpha with U beta. The previous discussion showed us how to get a Cartier divisor from a Weil divisor. Now we want to describe how to get a Weil divisor from a Cartier divisor. Let's call this Cartier divisor curly D. We want to associate to it some Weil divisor that looks like this. So we need to define what this order of vanishing means. What is the order of vanishing of this curly D at Ci? Well, let's take some U alpha here that actually intersect with Ci. And if we shrink U alpha small enough, then because we know Ci have local equation, right, we can assume that Ci is cut out by a single equation, G alpha. Now D on U alpha is cut out by F alpha, right? Then now it's easy. So we can factor F alpha to the maximum power here of G alpha, and then this should be a unit invertible along Ci here. So then we can define this order of vanishing to just be this Ni. In other words, this is the maximum power Ni, such that F alpha lies in this ideal. We can view this as an ideal of some local ring here, of any point here. And you can check that this is all well defined. A quick warning, in the previous discussions, we have been using the fact that X is smooth, right? If X is not smooth, we do not have that correspondence in general. But when X is smooth, we do have a correspondence between Weil divisors and Cartier divisors. This correspondence actually induced an isomorphism between the group of, this is the divisor class group, it's the group of Weil divisors, mod out by the principal divisors, and the group of Cartier divisors, mod out by the principal divisors. Note that here Cartier divisors are defined as equivalence classes. Two such families are equivalent if we can combine them to create another Cartier divisor, so if they are compatible. In the next video, we'll see the advantage of the Cartier divisors.